Good day to you all. It's Evan Snyman for Umifloco, Making a Difference. What I want to do today is use this idea of gradients and tangents to find what we now call stationary points, or what we used to call in the old parlance, local maxima or minima. The points on a graph where for a certain period of time, we have the highest point or the lowest point of the function. Okay, so effectively what we're asking ourselves is if we had a graph which was curving, okay, because of these arrowheads, we know that the range of this function actually is y is an element of real numbers, okay? However, what we can see is that in this zone over here, okay, in this zone over here, although this graph is heading off to much higher values further on, we can see that we have got what we would call a local maximum. It gets called a stationary point because if you think about it, the graph is increasing for a while, and now after this point, it is decreasing. So for the briefest moment, it must have stopped, changed direction, and headed off in a different direction. In the same way, I can have the argument that to the left of this point over here, okay, the graph was decreasing. To the right of this point, the graph is increasing. And so what I have in this zone over here is a local minimum, given that it's not the full minimum of the function, because we can see that this function goes down to negative infinity to the far left. So a stationary point is a single term to cover both the ideas of a local maximum or a local minimum. And the key concept is that along this function has got a large number of different gradients, okay? But at the key is that at the stationary point, this this tangent will be horizontal, okay? So at this point, the tangent is horizontal. So at the local maximum, which is one of the one of the types of stationary points, the tangent is horizontal. Now, hopefully you recall that what that means, and again, here we are getting our key ideas going, is that m will be 0. Put into our previous thinking, m is nothing more than f prime. Now, that gets us our local maximum, but it also would get us our local minimum. Okay, so the same method will help us find the local minimum. Okay, so again, for both these points, we have the gradient of n equals 0. Again, it should not surprise you that because both of these lines are horizontal, that they are parallel to one another. Okay, and for both these lines, the gradient will be 0 because, as we said, they are horizontal. So the key to finding a stationary point, okay, and again, this follows up some other work that we've done before, okay, to find an x-intercept, we know that we need to make y equal to 0. Okay, to find a y-intercept, we know we need to make x equal to 0. And what we're discovering today is that to find a stationary point, what I need to do is to make f dash equals 0. And there's a sort of symmetry or a sort of beauty to that idea that all we are doing to find all these key points on a function is making something equal to 0. We just need to keep track of which one it is. Again, if we made y 0, we would be finding an x-intercept. If we made x 0, we'll be finding the y-intercept. And if we find f prime and made that 0, we'll be finding the stationary points, in other words, the local maximum or the local minimum. Now, again, what is kind of interesting is that, again, if our original function was a cubic, so in the case of the one I've got here, if our original function was a cubic, we know that the shortcut tells us, okay, the rules of derivatives tell us that what we'll do is we will times the power to the front and drop the power by 1. So that means we know that the first derivative will be a quadratic and have an x squared option. Again, hopefully you are familiar with the idea that a cubic could have 3 x cuts, and therefore a quadratic should have 2 solutions. In the case of what we are dealing with here, the x values of those solutions are the x values of the stationary point. So a cubic function has a quadratic first derivative, so it should not surprise us that a cubic function would have 2 turning points or 2 stationary points, and as a result, again, another word for stationary point is a turning point. Apologies that I didn't say that earlier. And as a result, if it has got 2 turning points, it has this traditional S shape. Okay, there are certain conditions where this S shape is a little bit distorted, but generally speaking, a cubic function has this traditional S shape. Okay, with 2 turning points, one of which will be a local maximum and one of which will be a local minimum. Okay, so again, what we're trying to work towards is one of our key goals is to head towards being able to sketch a function. And again, I've found two old examples for us to look at, and let's work through them together. So, given a fairly straightforward function, please notice that it is missing a term. If we were to be looking at these terms in descending order, there is no x term on this particular function. Okay, and we are being asked to find its turning point. Again, we're asked to sketch the function, so I'm not going to sketch it initially. I'm not going to try and imagine what the sketch will look like initially. Okay. What I do know, okay, though, is that the y cut, okay, will still be 4. So the y cut will be 0 and 4. That is still clear from the fact that 4 is the constant of this function. Okay, that is more relevant for question B than it is for question A. Okay, so we've spoken about this. Turning points are found by making f prime of x equal to 0. So what I need to do is I need to do that. I need to find f prime first. Again, because it's quite a friendly function, it's not going to be too difficult. It's going to be 3x squared minus 6x. The plus 4 falls away to become 0. And we've got our derivative, but we need to make that equal to 0 to be able to find a stationary point or turning point, also known as a local minimum and maximum. So again, even though we've just done it quite quickly, there were actually 2 parts to this question. One was to find the derivative, and the second part was actually to make it equal to 0. To solve this thing is not overly difficult. Okay, we're going to get a common factor of 3x, and x minus 2 equals 0. So one of them is going to be, one of the stationary points is going to be at x equals 0, or the other one is going to be at x equals 2. Now again, we spoke about this just now. Because this was a cubic, we knew that the first derivative would be a quadratic and x squared function. And so again, it should not surprise us that we are getting 2 answers to our question. Okay. However, again, be careful. We have not completed the task yet. They did ask us to find turning points, and a point always has an x and a y value. So I need to go ahead and find y values. We know that y equals f of x, which means I'm going to plug this 0 value in. So if I had f of 0, okay, well, if I put f of 0 in, I would get 0 minus 0 plus 4. So I would know that my y value here is 4. So 0 is paired with 4. In the same way, I'm going to plug 2 in. So f of 2 equals 8 minus 12 plus 4, which in this case equals 0. So y in this case equals 0. So I know that this is paired 2 and 0. Now again, you should be screaming at me that the fact that this is 0 and 4, the fact that x is 0 means I have a y-intercept. And in the second case here, because the y value is 0, 2 and 0, because the y value is 0, I also have an x-intercept. So in part B, where they ask you to sketch this function, okay, we can do this quite powerfully, because we know that this function is going to have the following key points on it. It is going to have a turning point. So this is part B. It's going to have a turning point at 0 and 4. That actually is a turning point. Okay, so 0 and 4. At 2 and 0, we have another turning point. Okay. Now, the hint I'm going to give you is to remember that a cubic function tends to have this S shape. So what is going to join the turning point is that sort of S shape. Because this is a turning point, it is now going to head upwards to the far right. And because this is a turning point here at 0 and 4, it's going to head downwards to the far left. Okay. We don't know it for today, but our next question is going to involve finding that other x cut. Okay, so not for now, but coming up fairly soon, we're going to go on an investigation to find that other x cut. But what I want you to see here is that by finding the two turning points, I'm able to generate a sketch of the function. We would then normally go look for x cuts and y cuts. In this particular example, there came two of these. One of the x cuts and the y cut came along as freebies, and so we didn't need to go looking for them. But we would, in this case, normally, if we're trying to sketch this graph accurately, we'd need to go on a hunt to find that other x cut. Okay, I've got one further example. In this particular one, they've given us the picture and the equation of the function, and I just need to tidy up my handwriting, it looks like. I need to make sure that that looks like a square. Okay, so our function is f of x equals x cubed. So it's going to have this cubic function. Again, because it is positive, we know it is going to go up to infinity on the right-hand side, which means it has to have this shape with the local maximum occurring first and the local minimum occurring second. Okay, think this thing through. If I had minus x cubed, this picture would be upside down with the local minimum occurring first. Okay, they tell us that the 1x cut or the 1x intercept is 5. That is marked on the diagram. They want us to find the values of the other two x-intercepts. So in other words, they want us to find these two values over here. Okay, we want to find these two other x-intercepts over here. Okay, if they had asked us for the y-intercept, well, that would not have been a problem. We would know that the y-intercept would have been 0 and 30. So that's not an issue. We can see that from the plus 30. But having asked us for the two x-intercepts, we need to go ahead. Okay, and we need to find the values of C and D such that the point CD over here on the graph was a local maximum. And then we need to find the place where the gradient of the graph is -8. And that will be somewhere on this middle section here, because that's the part of the graph where the gradient is decreasing. So let's go have a look. Because we know that the 1x intercept is 5, okay, because we know that the 1x intercept is 5, okay, we should also realize that therefore one of the factors is x minus 5. So we therefore know that f of x, which is x cubed minus 4x squared minus 11x plus 30, we should realize that therefore this would equal x minus 5. And I now need to go ahead and try and work out the other factor. Now, there are many ways to do this, and I know we could have solved this using our calculator, if you've got the fancy calculator. Okay, we could do this using synthetic division. We could do this using a whole range of things, but I'm going to do it by inspection. Because we've got an x over here and we want an x cubed, my question to you is, what do I need to do to this x to get the x cubed? Sorry, I don't want that color. I wanted a different color. Okay, so what I need to do to the x to get the x cubed, hopefully you realize I need to multiply it by an x squared. In the same way, what I need to do to the minus 5 to get it to equal 30, hopefully again you realize that I need to multiply it by minus 6. Okay, so those two give me the outer two terms. I now have the x cubed and I have the 30. What I'm going to choose to do now is I'm going to pick one of those two, and I'm going to choose to pick the 11x minus 11x for no other reason than I just happen to feel like it. Okay, and what I'm going to look at now is, my question is to you, how do I get x's? And I get an x by saying x times a number or a number times an x, realizing that this term here would need to be an x term because it lies in between an x squared and a constant. So what I need to do is work this thing out. What is our coefficient here going to be in this particular example? Well, I know that x times minus 6 gives me minus 6x. I know that I want to achieve minus 11x as my outcome, so that means that this middle term would need to be minus 5x. Minus 5 times what would give me minus 5x? Minus 5 times plus 1. So I now know that that middle coefficient is plus 1x. What I'm going to do now is continue out my factorizing because I want to see my three factors. So what I now have is x minus 5. I want to factorize this trinomial. I'm going to get x plus 3 and x minus 2, which gives me my three roots of x equals 5, which I knew and expected, x equals minus 3, or x equals 2. So I now know that this one x cut is going to be at minus 3, and the other x cut is going to be at 2. Okay, this raises an interesting question, because again, what I'd like to see here is that this local maximum must lie in between the values of 3, minus 3, and 2. And in the same way, this local minimum, okay, must lie in between these two x cut values of 2 and 5. So in between any two consecutive x cuts must lie a turning point or stationary point, or at least the x value of one of those type of points. Okay, so what we're going to do now is we are going to look for the part B of this question. And so let's have a look at that. Okay, I now want to find the points C and D such that I have a local maximum. Okay, so we are saying that to find a local maximum, we have said this before, what we need to do is we need to find the first derivative and make it equal to naught. So again, let's do that. F prime of x for this particular function will be 3x squared minus 8x plus, minus 11. And we need to make that equal to naught. Again, I said to you earlier, that's actually two steps. One is to find the derivative, and two is to make it equal to naught. Having done so, we need to factorize this thing. So we are going to get x 3x and x. Okay, it would need to be 11 and 1. We would need to have minus 11 and plus 1 equals naught. As a result, x equals 11 over 3 and x equals minus 1. Now, again, our realization earlier that the local maximum is the left-hand value, whereas the local minimum is the right-hand value, should make us realize that this then is the value I want for my local maximum. So this here is the value I want, okay, to be able to get my local maximum, whereas the x equals 11 over 3 would be the value for my local minimum, my green value. So what we realize now, hopefully, is that therefore c equals -1, and all d is the y value. So y value is y equals f of x. So I need f of 1, sorry, f of -1, which in this case would be -1 -4 plus 11 plus 30. And what I'm getting out here is that y equals -5 plus 11 is 6, so 36. And again, what it tells us then is that d equals 36. And again, just a quick thought. If d is 36, that does make me happy because it is higher than the y cut of 30. So just a piece of common sense. If I've already got a y cut at 30, and this point is a turning point, it must have a value that is higher than the y cut because it is a local maximum. Okay, the last one is to find the point of the graph where the gradient is -8. So again, these questions tend to take a little bit of space, so let's go and have a look at it. Okay, last one. Okay, in this case, they're not asking us to find the gradient, they're actually asking us to find points where the gradient is a particular value. We've seen questions like this before, London, New York, and New York, London. So we know that f prime of x from a previous question was 3x squared. 3x squared minus 8x minus 11. They are telling us from here that they want to find one where the gradient is -8. So all I'm doing is I'm saying that this must equal -8. I'm going to solve that. Therefore, 3x squared minus 8x minus 3 equals 0. I'm going to factorize that down. So 3x minus 1 and x minus 3. No, it doesn't quite work. So I'm going to get plus 1 over here equals 0. And as a result, x equals -1/3, or x equals 3. Okay, so again, they've asked us for points on the graph. So they're saying over here at -1/3, this graph has got a gradient, a slope of -8. And we can see that at this point here on the graph is heading downhill. It's got a negative gradient. Over here at 3, we're not talking about the x and the y value. What we can see is that at this point in the graph has got a negative gradient. In this case, a gradient of -8. Again, please just make sure we answer the question. They've asked us to find points. Okay. Again, it does not surprise us that a cubic graph has 2 points when it comes to gradients, because the gradient will be a quadratic. And as a result, to find a y value, we're going to simply sub these things in. So therefore, f of -1/3 equals -1 over 27 -4 over 9 plus 11 over 3 plus 30 equals some answer. I'll work that out now. And f of 3 would equal 27 minus 4 times 9 is 36 minus 33 plus 30. So I've got net loss of what looks like 12. Okay, so the 1 point is 3 and -12. And the fact that that y value is negative suits my diagram. And so again, this is what I was hoping to find to discuss with you is, again, I'll get my calculator out, but when I do the sum here, I should end up with a positive value because we know that this is going to be a positive value. But interestingly, again, because that turning point is at 36 and that y cut is at 30, we should know that this answer we're going to get here, that answer should be less than 36 and greater than 30. Okay, so again, minus 1 over 27 okay, minus 4 over 9 plus 11 over, excuse me, plus 11 over 3. You have to use the calculator takes longer, is 33.185. Okay, so again, no major surprises that this answer has ended up being 33.185. And again, just common sense by looking at the diagram says that the answer had to be between 30 and 36. And so when we do get a value like that, we should move on with confidence, knowing that we have most likely got this question correct. Okay, thank you very much for your time. I hope to see you soon.